Hello dear students, and welcome to the second part or second video on topic 3, that is soil behavior. In the previous video we looked at what is stress and how we can calculate different types of stress in soil, that is total stress, water pressure and effective stress. Now in this video we're going to look into a bit more details of soil behavior in terms of stress and some other parameters that can affect it. Now, just starting with a recap on the soil behavior, the behavior of the soil mostly controlled by interparticle friction, and that is also dependent on effective stress that we learned in the previous part of the video, and that basically means higher the effective stress, higher the soil friction, or that is the friction force inside the soil is higher, and the soil will behave stronger. Just giving you an example, let's say we have a soil column. It should be a proper rectangle, but my drawing is not that good. Anyway, this should do the job. Now, if you take a soil element from here, let's call it location A. And if we look at another soil element here, let's call it B. What do you think? Which soil, considering everything else is the same, which soil will be behaving stronger? What do you think? Just think about it for a second. And the answer obviously will be location B. And the reason behind it is location B, the soil is under much higher effective stress. That means these interparticle forces are much higher, and that means it is very difficult, or it is much harder to displace these particles, to move around these particles. And that means the soil will be basically stronger. And one of the basic assumptions we make in soil mechanics is basically the soil particles, they are indestructible and the water is incompressible. Now, from here, we'll be looking at an example, again, that is related to effective stress. This is what happened in Christchurch, and this will probably give you a slightly better idea why effective stress is so important and how it can control the behavior of a soil. Now, the first picture, a broken building or destroyed building, that's not my part, that is dealt with the first part of this course, that is superstructure. We'll be talking about this thing, why this happened. What happened in here? Probably the car was parked in there and then something happened in this location, what we call liquefaction. Liquefaction is basically the point at which the soil loses all its strength. How it might happen? Let's say, if you remember the friction theory, I'll just write the equation in here. Friction force equals to a constant K times normal force. That is, if we have two particles, the interparticle friction force between these two particles is a function of, or depends on, a friction coefficient that represents how rough these two particles are. And the second thing that controls it is the normal force acting at this plane, that is in this direction, the force in this direction. Now, what happens during an earthquake? Let's go and see a location. This is a cross-section, or how the soil profile looks like under somewhere in Christchurch. That's the location you can see in here. And now let's say this is all sandy type soil. And if an earthquake strikes, let's say we have a structure on top of the soil as well in there. If an earthquake strikes, what happens? These soils are agitated vigorously, they are shaken vigorously. And what does that mean? The water inside those soil particles, they also get agitated and gets a lot of energy. If the water gets a lot of energy, what does that mean? The water pressure U is going up. Now, if we look at the effective stress equation, the total stress is not changing. Say the weight of the house is not changing, the weight of the soil in here is not changing, but what is changing is the water pressure. It is going up because of this shaking or agitation. The water has got some extra energy, now the pressure is going up. So what will happen if that goes up significantly? And that might mean at one point this can become close to zero. So what will happen if that becomes 0? What is happening to the interparticle, say these two particles and the contact force? F was equals to K times N. So if the force N becomes 0, which is basically sigma prime in this case, there is no friction force in between two particles. And if there is no friction, that means the soil has no strength. And what does that mean is the soil is now behaving like a frictionless material, that is fluid or liquid. And that's where this term soil liquefaction comes from. And that's exactly what happened in Christchurch. Now, it is very common in earthquake-prone area, in sandy, gravelly, this type of soil. It is not that common in clay soil because the pore sizes or void sizes inside a clay particle is very, very small, and it has a lot of cohesion as well, the stickiness in between particles, and that prevents it from getting liquefied. And once liquefaction happens, a structure will sink like that, or you can remember the previous picture, the car was about to sink into that hole where the liquefaction phenomena happened. Now let's move forward. I'll just briefly mention it here. I won't go into any more detailed discussion. The stress in soil, or effective stress in soil, as we have seen, is a function of total stress and water pressure. Total stress and water pressure, any of these two changes, the effective stress will change. Now in unsaturated soil, because of capillary suction, surface tension forces, if you remember from high school days, the water has lots of surface tension forces, and in unsaturated soil you will see air bubbles like this inside the soil. Now what happens in here? In here, these tiny pores, maybe there is a tiny pore in here, a tube-like thing, and then that acts as a meniscus, and how that is relevant to surface tension force. Now if you remember from your high school days, if you put two tubes in water, one is a bit fatter than the other, say this is 2 millimeter diameter and that is 10 millimeter diameter, the water will not stay here, it will start rising up as if some imaginary force is pulling them up. That is basically the surface tension force. So it is pulling the water that way, and that is exactly what is happening here as well. So it is pulling that way, it is pulling that way. So something inside the soil is pulling the particles together. We call it suction. We can also call it minus U, negative water pressure as well. See what will happen if the water pressure gets negative. Looking at effective stress equation, sigma minus U, negative U. That means if we have some suction, our effective stress is going up, and that means only one thing: the soil is getting stronger. Anyway, we'll leave all the discussion in here. We'll be able to learn a little more about it when we are talking about footing, but that's where we'll leave the unsaturated soil and its effective stress and capillary action. The discussion, we'll leave it here. Moving forward. Now, we have just mentioned a few minutes ago, I have said, in soil mechanics, we assume the soil particles are incompressible, and so as water. Now, how a soil might fail? We're just saying the soil particles are incompressible, they're not breakable, so how a soil might fail? Again, they're not incompressible or indestructible, but within a range of engineering interest of stress, let's say 10 or 20 kPa to few megapascal, it is sort of true, and we always try to make our life easier, calculations easier, so we use this assumption to make our life easier. Now, if that is true, how a soil might fail? Let's see, let's take an example of this slope failure. Some slope failure happened here. Now if I redraw it, it's a slope instability problem, something like that happened. A chunk of soil like this just came sliding down. Let's look at just a small section of this, and if we magnify it, what we will see, a layer of soil has to slide past another layer of soil to make a failure like this happen. That's where the strength of the soil, we call it shear strength. It's basically all the failure of a soil happens because of some layer is shearing past the other. If we look at a footing problem, so we have a footing and it is applying downward load. So that what that will mean, it is pushing the ground this way, and some soil will try to slide that way, and some soil will try to slide that way to resist that force. And the soil outside will have to resist it back. Now, if the strength of the soil is not enough, what will happen? This soil will slide that way and show up on the top. That will mean the footing will be failing. Again, the shearing of soil is leading to its failure, and that's where the word shearing strength or shear strength comes from. Anyway, how to calculate shear strength, or what it depends on? It depends on a number of things. Obviously, the stress, also the density, and the friction angle and cohesion. These two are new terms for you. We'll talk about it in another video later. How strength affects the shear strength, we have just learned. It's basically a frictious force between two particles, and then the stress are higher, the friction is higher. That's one thing. And we have also learned about density in another previous video. Say if we compare this soil to that one, say this is a much denser soil, and see how compactly packed there. Now one layer, let's say the top layer, has to slide that way, and the bottom layers, let's say, will stay still. This will be much harder in this case compared to this one, and that's where density plays a part in it. Friction angle, we have just said. Friction angle is a fancy term we use to express how angular or frictious or how rough the particle surfaces are. Now, if you compare these two particles to those two particles, you will see if we have a particle set like this, they will be much rougher. That means they will have obviously much higher strength. And if we have particles like this, this will be much more difficult for one layer of soil to slide past the other, because the surfaces are very rough, and that is increasing its friction resistance. Now, how we calculate the strength of a soil? We all obviously call it shear strength, and this is a very common equation we use to calculate the shear strength. Tau, this is a symbol tau we use to denote shear strength, and C and phi are what we call cohesion and friction angle. We'll see in another video what they exactly means, or in the later part of this video what they exactly means. And sigma is obviously the stress quantity we have learned before. Now there will be a couple of examples done. You can go and have a look at them later, and there will be a couple of exercise problems related to this, and as well as some problem related to effective stress calculation as well. So make sure you go and attempt them and compare your solution against the solution provided. Now, how do we get C and phi? There are many different ways to get it. First of all, the most reliable one is obviously to do some laboratory tests, and we'll specifically look at one of the tests. And then we can use some correlation. If we know the plasticity of a soil, we can correlate. If we know the type of a soil, we can correlate. And the third thing, again, you might laugh at it. We make a guess, educated guess, but that is not a very uncommon practice to do. And an experienced geotechnical engineer knows what number to use. Anyway, this is one of the tests we can do to get C and phi. Basically, what we call is a direct shear test. What we do, we have a split box, two halves. That's top half, that's the bottom half. What we do, we put some soil inside, we apply some load vertically downward. So we'll put some soil and put a plate on top and apply some load and try to push the top half slide past the other. So what will happen? This will simulate. Oh, no, that's the wrong direction, probably. It is moving that way. I'll just find the eraser. Don't worry about it. It's moving that way. So what is happening in here? Along this plane, the shearing is happening. And then we have this normal force, and we have this shear force, or how much force we need to slide past. And if we increase normal force, this force will be higher. We increase it further, this will be higher again. So you can repeat this thing with a number of different normal force and find out what is the sliding or shear resistance, and then we can use them in a diagram and plot them and get what is C and phi. We'll see what are they in the next slide. Let's say we have 3 tests. One is done under half a kilo of normal force, half a kilogram per centimeter square, and the second one was done at 1 kilogram, and the third one was done at 1.5 kilogram. And you can see in here at 1.5 kilogram, the shear stress or shear resistance was much higher compared to 0.5 kilogram. And if we take the peak points and plot them, normal stress against shear stress, we can draw a line. And the slope of that line is basically phi, and this intercept, we call it cohesion intercept, or C. So this can be true for one soil. If we have a different soil, we might have something like that. So for different soil, the slope and the intercept cohesion will be different. And doing this test, we can find out what is C and phi and use it. If we can go back to that equation, use it in this equation to find out what is the shear strength of that particular soil. And here are some typical values of C and phi. We sometimes will use, if we know the soil type, we'll use a chart like this to come up with a rough number what a C or phi value might look like. This is another chart. This is from AS 4678, Australian Code for Earth Retaining Structure, and you can see it has classified the soil into a number of categories, and then there are different types of soil. And if we know the soil type, we can at least come up with a range of values and pick a number within that range to say this is C prime and this is phi prime, or C or phi, and use it in the Mohr-Coulomb equation to find out what is its strength. We'll leave it here, and please make sure you go and look at the example problems and attempt the exercise problems. This might be very important for your assignment. Thank you very much for watching. Our next topic will be on subsoil investigation, where we talk about how we extract a sample from the soil and what are the things we do, what are the process or steps we'd have to take to collect information about what is lying underground. Thank you very much. See you next time.